This is lecture number 25 of my series on advanced mathematical physics, where we are studying differential geometry at present. In the last lecture, we met a very important operation on differential forms, the operation of an exterior derivative. The definition of the exterior derivative looked a bit complicated, especially when we tried to put it in a coordinate independent manner. Let me remind you that this exactly was how the exterior derivative d omega of a k-form omega was defined, and frankly the expression is quite complicated looking, and we had promised that we are going to justify why this has to be the expression for d omega in a later lecture, but that lecture is not for today. Today we want to explore the exterior derivative a bit more, but let me remind you that we had already done the following in the last lecture. We had seen that this expression can be simplified, or at least takes reasonably simple forms, when omega happens to be a zero form, that is a function, or a one form, or a two form. And at least for lower order forms, for a zero form and a one form, we had shown that if you apply d twice on omega, the result vanishes. From that, we sort of speculated that d square omega could be 0 for all omega, that is d square vanishes and d is what is called a nilpotent operator. But note that I have put this within question marks here simply because we don't know that for sure. We have just seen that to be true for the cases where omega is a zero form or a one form. Another thing that we had seen is that this apparently complicated formula for the exterior derivative actually became rather simple when expressed in terms of coordinates. When you are using a coordinate system with coordinates x1, x2, xn, then a k-form omega can be expressed in this particular fashion in terms of the component functions omega I1 through ik and written as omega I1 through ik times dx I1 wedge dx I2 up to wedge dx ik. Now, if this representation is used, it turns out that d omega, the exterior derivative, has this very, very special and simple form. You just do an exterior derivative on omega I1 through ik, the component function, which essentially means you just calculate its differential one form and wedge that with the rest of the dxi's here. So this part stays unchanged. You just do a d on this and wedge it, remembering of course to keep the order intact because one forms have wedge products which do not commute, or rather they anti-commute. So in order to keep the signs correct, all the orders has to be maintained clearly. Now notice that despite the fact that this is a rather simple expression, there seems to be a problem here, and that is why I have put a question mark around this. There are two issues. Firstly, the proof that d omega is given by this, which was given in the last lecture, is one that I really don't like that much because it's a bit complicated. There are easier ways of establishing this. But much more importantly, in that proof, we had assumed that if you have a k-form and carry out an exterior derivative on that, according to the definition given, you are really going to end up with a k plus 1 form. That part was critical to the proof of this expression. Now, what is conceptually very important is to realize that although we started by stating that the exterior derivative takes a k form to a k plus 1 form, we had never actually proven that fact. We have stated an expression for d omega, and using that expression, we should be able to derive that this is really a k plus 1 form. Not doing that was a very big omission that our previous lecture suffered from. Today, let me begin by first trying to correct that. In order to establish that, let us first ask ourselves exactly what we need to prove that d omega is really a k plus 1 form. Firstly, it has to be a 0 k plus 1 tensor field. So you should be able to take k plus 1 vector fields and produce a function. But it has to do this production of a function in a multilinear fashion. Not only should it be R-multilinear, it should also be C-infinity multilinear. That is, if we were to replace any one of its arguments by a linear combination with real numbers, you should be able to express the result as the corresponding linear combination of the individual vectors that went into that particular component. Also, if we were to replace any one of the arguments by a smooth function times a vector field, that smooth function should be factorizable. You should be able to pull it out of the entire expression. Being a 0 k plus 1 tensor field is not enough. It also has to be smooth. Finally, we come to what really makes it a form rather than any other tensor field. It has to be completely anti-symmetric in all its arguments. That is, if you were to interchange any two of the vector fields that are being supplied as arguments, the result has to change sign. We should be able to establish all of these starting from the definition of d omega given in this particular manner. We are going to do that, but not in the same order in which we stated them. We are going to start with the last one first. Let's begin by showing that this expression is completely antisymmetric. Interchanging any two of the vector fields, let's say xa and xb, in the argument list is going to produce a minus sign. This may seem to be quite simple to do, given the fact that omega is already known to be a k form, so omega has to be completely antisymmetric in its k arguments. However, it turns out that the complete argument for antisymmetry of d omega is rather non-trivial. Let us first try to state exactly what we are trying to do here. We will start with this expression where I have indicated the two specific vector fields that we want to interchange, and a and b here are just the indices which tell you at which point in the argument list these particular vector fields occur. So a and b are basically positive integers between 1 and k plus 1, and a has been taken to be less than b, so that the one field that has been indicated by xa is sitting to the left of xb in the argument list. What we want to do is compare this with what happens when we interchange the two vector fields xb and xa. What is important is to realize that the positions a and b stay the same. It is the vector fields which occupy them that get interchanged. So xb is now sitting in the 8th place and xa is sitting in the bth place. We will now take a look at this expression and try to see what changes there will be when this interchange takes place. Now, if we look at the first sum, then if neither a or b is equal to I in this sum, then what has happened is xa and xb are arguments to omega which we have interchanged. And omega being a k form, any interchange of its arguments gives you a minus sign, and xi being linear in its action on the function omega acting on this, you will get an overall minus sign. So, all those terms where I is not equal to either a or b will change sign. At this stage, we have two more terms remaining in this sum. The terms where I equals a and b respectively. So this is where I have written down both of these terms. So this is a term for I equals A, where I have also shown the position of xb, just because that's going to be useful later. And this is the term for I equals B. Again, the position for xa has been shown. Now this is the original sum that we had. And now we are going to compare this with what happens when we interchange the vector fields xa and xb. Note that it's only the vector fields which are being interchanged, not the positions themselves. So these labels, these numbers which depend on the actual position of the vector field being taken out, that does not change during the interchange. So this term gives rise to minus 1 to the a plus 1 xb. Of course, this xb becomes xa, and this place, which after all is really missing, had x hat a before, now it has x hat b. Remember, the hat simply means that this is missing from the argument list. A very similar thing happens here. Now, our goal is to show that the overall sum changes sign, which must mean that these two together must change sign under the interchange of xa and xb. Now, in order to see this, let us focus on this term. Here, you have the missing xb, and then you have a bunch of vector fields which really are xa plus 1 all the way up to xb minus 1 sitting here. So the number of vector fields between this position and this position is simply given by b minus 1 minus a. So that's the number of vector fields you have in between this location and this. Now, in order to make this term take the same form as this one here, I need to push the xa forward until it comes and sits here. That means it has to cross b minus 1 minus a number of vector fields, picking up a minus 1 every time. Remember, omega being a form is completely anti-symmetric. Every interchange gives you minus 1. So once you do that, this expression essentially becomes the same as this one, with xa sitting instead of here, right in front, as in here, and you have an extra factor of minus 1 to the b minus a minus 1. Now if you take a look, these two cancel out. So you are left with minus 1 to the power b, which essentially means that you have recovered this term but with an extra minus sign. A very similar thing happens for the other term. Here, after the interchange, you have got xb here, whereas you really want an xa in this location. Or rather, you want the xb here, and this is where the missing xa should have gone. So once again, in order to make this look like this, you have to push the xb back through, again, exactly that many vector fields. So the same factor would come about. And now the overall factor that you have, note, is simply minus 1 to the 2b minus a. Minus 1 to the 2b is of course 1. And minus 1 to the minus a is the same as minus 1 to the plus a. So once again, you have recovered exactly this term but with a minus sign. So these two terms together change sign under the interchange, and as a result, the first sum in the definition of d omega changes sign when you interchange two vector fields here. We now have to focus on the second sum here. The second sum is slightly more complicated to work with, but as long as you keep track of which term is going where, it's pretty straightforward. Now it's rather obvious that if I and j, the two indices of the summation, were both different from a and b, then xa and xb would be vector fields sitting inside this lot. So these would be arguments of the K form omega. And therefore, interchanging xa and xb in that case is simply going to give rise to a minus sign. Also, if I happens to be equal to a and j happens to be equal to b, then xa and xb are together sitting in the Lie bracket in this term, and then interchanging xa and xb would definitely give you another minus sign, the Lie bracket being anti-commuting. So the tricky terms, the ones which we still have to work on, are the ones in which precisely one of either xa or xb is sitting inside the Lie bracket. Of course, that means that one of the I or j happens to be either a or b, and it's still going to be a summation over the other summation index. So we will have to deal with two sums, one in which xa is inside the Lie bracket, the other in which xb is inside the Lie bracket. But let us now break up these sums into pieces. You will see why this breakup is important soon. Let's first look at the situation where xa is inside the bracket. Now you can have three possible scenarios. One is when you are summing up I from 1 to a minus 1. So I is less than a here. This is the standard obvious term that you get when you put in j equals xa. Now, there is another possibility. I could be, at least the lower summation index could be a, and the upper summation index, which could have been called j, but since it's a summation index, I have called this I again, is here. So it's a square bracket xa comma xi, and xa and xi are missing. But the important point is that this missing xi is actually occurring in this argument list before xb. And that means I here lies between a and b. And the final possibility is when I is more than b, once again the Lie bracket is xa comma xi, and the missing xi is going to sit beyond xb in the list. So these are the three terms in which you have xa in the Lie bracket. Similarly, you will have three more terms which you are calling T4, T5, T6 respectively, in which xb is sitting inside the Lie bracket. Once again, one is where the summation index is less than a. So the xi is actually sitting before xa. Again, you have another situation where a and b are bounds for the I, and that means that once again you have xi comma xb, b still being more than I, but the xi hat here, the missing position, is between xa and xb hat. Finally, T6, the last sum, is actually when I happens to be more than b. Sorry for the mistake there. And you have omega xb comma xi. Now because I is more than b, the Lie bracket here is xb comma xi. And you have xi hat sitting all the way out there, beyond xb hat. Now, let us take a look at what happens to these terms when we interchange xa and xb. Now there are 6 terms to look at, and I am not going to show you what happens to each one of the 6 terms because that's simply going to take too much time. But the basic idea is the same for each of these cases, and you have to just be careful about where each vector field is going. So let us start with T1. If you were to interchange xa and xb here, of course you will end up with xb here. This will become xa and this will become xb hat. So T1 would essentially give rise to this. After the interchange, it will become T1 prime, and here instead of XA you have XB, instead of the XB you have XA, and of course the missing location where X hat A was before, or rather XA was missing from before, you have XB missing from that position. Now, between this point and this point, remember this is actually the 8th location. Between this and this, you have XA plus 1, XA plus 2 and so on up to XB minus 1. These are the vector fields sitting here. So, once again, a total number of these vector fields is B minus 1 minus A. So, in order to make this look like one of the terms here, and since you have a square bracket xi, xb and I less than A, you expect it to look like this term, T4 here. What you need to do is to make the XA move until it sits here, which is what its location is in T4. Everything else is the same between T1 prime and T4. So, if you do that, you are going to get an extra factor. You are going to get this extra factor minus 1 to the power B minus A minus 1. Simply because you are making B minus A minus 1 interchanges. That ultimately leads you to an expression like this, where you can see that this is exactly what you have in T4. The only difference is in the P factor. The P factor here is minus 1 and the A's cancel, so you have I plus B minus 1. So minus 1 to the I plus B with an overall minus sign. So this exactly becomes negative of T4. The other terms are very similar, but let me just show you one more term just to reveal a bit of subtlety that could be there. This is the case of T2. T2, remember, was this term. And you want to interchange A and B once again here. So XB will be sitting here. And X hat B would be sitting here. That is, XB will be missing from this location. XA will be sitting here. And here, of course, you will have XB, XI. Now, since this is a term where I lies between A to B, you expect that this is going to give rise to a term with similar limits here. That is T5. Well, essentially the same thing happens here, but one important point has to be kept in mind. Between this location, which was where XA plus 1 was sitting, and this location, where originally you had XB minus 1 and is still there, because you have not changed those vector fields, you had B minus A minus 1, this many vector fields. But now you don't have that many. You actually have one less because the xi is missing and the xi is somewhere in between these two. So, the interchange that you have to carry out, the series of interchanges, so that the xa ultimately moves here, so that the whole thing looks exactly like T5, requires B minus A minus 2 interchanges, so this sign comes in, and now, since minus 1 to the minus 2 is of course plus 1, you have minus 1 to the I plus B. So it looks like you are getting exactly T5, but note this very carefully. In T5, what you did have is xi, xb, this Lie bracket. Remember, B is more than I, and the larger one, at least in the original sum, the larger one sat to the right. But here you have xb, xi. Simply because this was xa, xi in the original, and xb has just come in its place. So note that if you were to rearrange this to make it look like T5 by interchanging these two, you end up with a minus sign. So T2 changes over under the interchange to negative of T5. And by following the same kind of reasoning, it should be pretty easy for you to show that each one of these 6 terms change sign to some other term under the interchange, and so the overall sum just changes sign. So d omega, as defined, is really completely antisymmetric. Everything changes sign. That was quite a bit of work, and I would urge you to go through each one of the 6 terms that we have written down and convince yourselves that the whole thing really changes sign. Now, just in case you found the previous discussion to be too complicated and are feeling a bit discouraged at the prospect of going through proving more properties, let me rush to assure you that the hard work has mostly been done. Establishing the antisymmetry, complete antisymmetry of d omega according to this definition is perhaps the hardest part of the job. Let us now turn to the other properties that we need to establish before we can claim that d omega is a k plus 1 form. And the first one of this is to show that it really is a 0 k plus 1 tensor. That is, it transforms functions, k plus 1 vector fields, into functions and does so in a multilinear fashion. First, let us prove the R-multilinearity. That is, if I were to replace any argument in the list of k plus 1 vector fields by a linear combination of 2 or more vector fields with real numbers as coefficients, I am going to get the corresponding linear combination of the resulting functions. What helps us to show that is the proof that we have just now completed. We have shown complete antisymmetry in all the arguments. And a bit of thought will convince you that this means that we don't really have to show multilinearity. All we have to show is linearity in any one argument. Because if, say, I wanted to show linearity in the ith argument, all I would have to do is interchange the ith and the first at the expense of a minus sign, prove linearity for the first, then interchange the ith and the first arguments in the pieces once again, and the 2 minus signs we get in the process, once we did the first interchange and again when we put them back, should give you an overall plus sign. That is, establishing that the expression is linear in the first argument, say, is enough to prove that it's linear in all the arguments. So we will prove it only for x1. Now, when we are trying to do this, note that this is the definition where I'm going to replace x1 by, say, ax1 plus by1. Now, when we explore these terms here, there will be essentially 2 kinds of terms for each one of these pieces. One in which I is equal to 1. So that's the term which has been replaced by the linear combination. That is, you are going to get ax1 plus by1 sitting here. And omega will act on x2, x3 all the way up to xk plus 1. There will be an overall factor of minus 1 to the power 1 plus 1 here, which is, of course, the fact that the first term always comes with a plus sign in the alternating scheme of things. And then you'll have to follow it up with a situation where I runs from 2 to k plus 1 all the way up to each and every one of these vector fields, where the xi is taken out, but x1, the one which has been replaced by the linear combination, is still going to be the first argument in the list of arguments for omega. What about the second sum? Here, since I is less than j always, the only possibility for I or j to be 1 is I has to be 1. And therefore, you have again 2 kinds of terms. One in which I equals 1 and j is anything more than that. So j actually runs from 2 to k plus 1 in this sum, where the first argument in the Lie bracket has been replaced by ax1 plus by1, and the other is when I and j are both more than 1. Of course, j is still more than I, and you get xi comma yj, xj, and ax1 plus by1 sitting in the second argument. It has not moved from its original place in the sum. Now, the rest of the argument is actually pretty straightforward. It's very, very easy to show that each and every one of these four terms, this single term and these sums here, are actually linearly decomposable. That is, they break up into two pieces, one with a times what would happen if x1 were alone, and the other with what would happen if y1 were alone multiplied by b1. So, the linearity in this case is very easy to establish. For the argument number 1, of course, as we have argued before, proving linearity for argument number 1 is enough to prove R linearity in every one of the arguments. So, proving R linearity was pretty straightforward. Proving C-infinity linearity would be slightly more complicated, but once again, let me point out that you will only have to worry about C-infinity linearity in one argument because of this complete anti-symmetry. So, just like before, we are going to choose that argument to be the very first argument. So, we are looking at the action of d omega on a bunch of vector fields in which the first one, which used to be x1 before, has been replaced by f times x1, where f is a C-infinity function. Now, according to our definition, this expression breaks up, just like before, into four terms. The first sum in our definition gives rise to the first two terms in blue here, and the second double sum over I and j gives rise to this, the green terms here. Now, if you look at the first sum, that comes in two kinds of terms. One in which the very first argument, in this case f times x1, acts on omega, acting on the rest of the arguments x2, x3 all the way up to xk plus 1. Then you have another piece, in fact the rest of the sum, where the sum is over I running from 2 to k plus 1, which means f times x1 is the very first argument which is sitting in the argument list of omega, and the ith xi has gone missing from this argument list and is instead acting upon the result of omega acting on fx1, x2, etc., all the way up to xk plus 1. The double sum over I and j also breaks up into two kinds, one in which I, the first argument, happens to be 1. So j starts from 2 all the way up to k plus 1, and you have x1 missing from this list, so this list actually starts with x2 here, and fx1 is actually inside the Lie bracket with xj. And finally, you have one more term where I and j are both more than 1. Of course, j is more than I. And that means fx1 is the first argument after the Lie bracket in omega. Now, if you look at these four kinds of terms, it's rather obvious that the very first one has a factor of f outside, and this one, because of omega's C-infinity linearity, also has a factor of f which you can pull out. So the very first and last terms of this and this, are obviously C-infinity linear. We have to pay attention to the other terms. Now, these are the two terms that we have to look at. And here, the first piece is easily seen to be xi acting on f times omega acting on the rest of the arguments, simply because omega, as we have said over and over again, is a 0k tensor, so it is C-infinity multilinear. On the other hand, this Lie bracket here breaks up into this expression, which is a pretty straightforward thing that we had derived before. If you have forgotten how this works, just think of fx1 Lie bracket xj acting on some function, let's call it g, work it out, and it comes out to be fx1 acting on xjg minus xj acting on fx1 time acting on g. And this, of course, is f times x1j, product of two functions, and xj, because of the derivative property, breaks it up into two pieces. Using this, you will get that this result, this fx1 Lie bracket with xj, actually is equal to this, because their action on any g are one and the same. Now, what we get to do here is notice that this, again because of the derivative property of xi's action, breaks up into two pieces, one in which f gets pulled out and xi acts on the rest, the other in which xi acts on f, and you multiply the result with omega acting on x1, x2, etc. Now this is what would have broken C-infinity linearity. That's one term where f is not being pulled out. However, look at the second sum. Here, this breaks up into two pieces, and the first one has an overall f coming out. The next one has xjf sitting here. And if you look at this carefully, you will find that this piece, the one you get when xi goes and acts on the f, and this piece actually give you exactly the same result up to a minus sign. And that means that these two pieces, which would have broken C-infinity linearity, cancel out, and all the pieces actually have a factor of f coming out from the sums. And therefore, the overall result is simply this. If you replace the first argument of d omega by f times that argument, the result is f times the result of d omega acting on the original arguments. So d omega is C-infinity linear in the first argument, and of course, because of complete anti-symmetry, that guarantees C-infinity linearity in all the arguments. So we are now very, very close to proving that d omega is actually a k plus 1 form. There's only one small thing that's left, and that's showing that d omega is a smooth tensor field. Now, that follows immediately from the fact that omega is smooth, and if you look at the definition of d omega, in particular d omega acting on this bunch, you can easily see that on the right hand side you have either omega acting on a bunch of smooth vector fields or some differentiable smooth vector field acting on some smooth function, which you get when omega acts on them. In either case, it's easy to see that every term on the right hand side of the definition actually is a C-infinity function. So d omega acting on a bunch of smooth vector fields does give me a smooth function, and therefore d omega is by definition a smooth 0k plus 1 tensor field. So the fact that d omega takes in k plus 1 smooth vector fields and produces a smooth function, both R-multilinearly and C-infinity multilinearly, proves for us that it is a valid 0k plus 1 tensor field. Smooth 0k plus 1 tensor field. Now, in addition to that, we have already seen that it is completely anti-symmetric. So that completes the proof that this really is a k+1 form. So the statement that we started last lecture with, that d omega is a k+1 form, has finally been validated from the definition itself. Well, not only that, this proof also helps us give validity to a proof that we did in the last lecture again. This was the proof of a very, very useful result, that if omega is expressed in terms of component functions, omega I1 through ik dx I1 wedge dx I2 up to all the way up to wedge dx ik, then d omega is simply the differential of the component function omega I1 through ik wedged with the rest of the basis coordinate differentials dx I1 wedge dx I2 all the way up to wedge dx ik. Now this result was proven in the last lecture under the assumption that d omega really is a k+1 form, and today's proof of that fact gives validity to the proof that we did in the last lecture. This result actually gives us a very powerful and simple way of calculating the exterior derivative of a k form. It will help us do practical calculations. Not only that, it will also help us to establish a lot of important properties of the exterior derivative. We will discuss many of these in the next lecture. Bye for now.